Okay, so what we want to show, what we want to discuss, is something that we saw in the examples in the previous discussion. We saw how we defined operations on linear maps, addition of linear maps, multiplication of linear maps, which was composition, and inverse linear maps. Okay, those operations we defined, and we saw that when we have the maps given by matrices, there's a compatibility. In the examples we saw that. So adding the matrices is the same as adding the transformations. Multiplying the matrices is the same as composing the transformations. Okay? So now we want to say this in general. We want to say that these are theorems, that this is in fact a general case. And the examples are, if you got the examples, you got the idea. Okay? Now it may be a bit blurred because the notation is going to become a bit heavy, because instead of writing A, we're going to write T, its matrix representation with respect to a base E. Remember our notation for matrix representations. Okay, so the notation is going to become a bit heavy, but the ideas are very simple. The ideas we saw in the examples. And before we start, I want to remind you of a theorem that we had. It was kind of hidden quite a while ago. But it's gonna be a very important theorem for all the proofs that we're going to see in this clip, and it's the following. We proved that if for any v, for any vector v in a vector space, AV equals BV, then A equals B. Do you remember this statement? It was rather long ago. You can look it up. But we proved that if for any vector in a vector space, AV equals BV, but for every V, not for some V, for every V, if they're equal, then the matrices coincide. Okay? The proof of this was not difficult, but it relied on some previous argument that if AV equals 0 for every V, then A is the zero matrix. Okay, and that was where the facts were hidden. Okay, so this followed from that just by saying, okay, if this is true, then AV minus BV is 0, and therefore A minus B is 0, and therefore A equals B. Okay, but how do we know that if A minus B times V is 0 for every V, then A minus B is a zero matrix? Okay, that's where the work is hidden. Okay, so if you don't remember this, you're going to have to go back and look it up, but we proved this. Okay, and we're going to use this. Okay, so here are the theorems that we want to show. The first one is the following. The first one relates to addition and to scalar multiplication of maps and their corresponding matrices. So let T and S both go from V to W, be linear, and let take E and F bases for V and W respectively. So E is a basis for V, F is a basis for W. Okay? Then the statement is, 1, if you add the two maps and take the matrix that represents them with respect to the bases E and F, right? In order to find a matrix representation, we need a basis for the domain and a basis for the range, and we know how to do this, right? We act on little e's, and we write what we get as linear combinations of little f's, and then we set them up as columns. That's going to be the matrix representation. Remember we did that? Okay. So the statement is that this equals the matrix representation of T plus the matrix representation of F. Okay? And 2, if you take alpha t and take its matrix representation, that equals alpha times the matrix representation of t itself. So do you agree that what this theorem says is precisely what we had in the examples? When you take matrices that represent maps, addition of maps translates to addition of the matrices. Scalar multiplication of a map corresponds to the scalar multiplication of the representing matrix. Okay? That's the statement of this theorem. How do we prove it? So let's prove it. Proof. Let's start with 1. So the way I'm going to prove it is using the theorem I mentioned in the reminder. I'm going to show that if I take a vector, and put it here, or put the vector here, so act on it by this matrix, or act on it by the sum of these two matrices, I get the same thing for every vector. And then it follows that the matrices are the same. Okay? You with me? Let's look back at that reminder. Here I'm going to take the right-hand side of the equation I claim is true in 1. Here I'm going to take the left-hand side and show that they're equal for any v. And it will follow that the matrices are equal. Okay? So let's do that. I'm going to take t plus s, find its matrix representation with respect to these two bases that I chose. Okay? And then act on a vector. But on which vector am I going to act? Which vector?
General.
A general one, but it has to be a vector. Not in V. This is a matrix. V can be a space of polynomials. In which world is the vector that I'm going to operate on B?
In V.
Not in V. T plus S know how to act on V. But this is the matrix representing.
Matrix. Okay.
So where is that vector going to be?
The coordinate space.
Right, in the coordinate space of V. This can act on VE. Any V, but it has to be its coordinate vector. That's what this knows how to act on. Good? And what I'm going to show is that this equals to this acting on VE. Okay? Good? Is it clear? Again, many times, at least half of the work is in understanding what you need to show. Okay? So does everybody agree that this is what I want to take? Okay? This is the A and this is the V. Okay? So by the theorem that tells us what the matrix representation does, we know that this equals exactly do t plus s to the vector v, but take that in its coefficient vector in w with respect to the base f. Do you agree?
I didn't get that.
This is precisely the theorem that we had last time. That's what the matrix representation does. Okay? You take the matrix representation, you act on a vector in the coordinate space, okay? You get what the linear map would do to the vector in the coordinate space in the image. Okay, that's what was this is precisely the theorem we had last time, and I told you now you're freaking out, and you said, "No, we got it. We're not freaking out." Remember that? Yeah. This is it precisely. Okay? Everybody good? Okay. So now what happened now is that we translated the sum into the sum here. These are different. Now we can work inside the brackets. Now we can work with the operation. Now we can work with the operation on the maps. And we know what t plus s of v is. By definition, t plus s of v is t of v plus s of v. That's what t plus s of v is, right? And all of this is something that lives in w, and we're taking its coefficient vector with respect to the basis of W. Good? Okay. Now, coefficient vectors, this is when in our very first discussion of coefficient vectors, before we knew anything about linear transformations, we said that the coefficient vector is linear. If we add two vectors and take their coefficient vector, it's the same as taking t of v, its coefficient vector with respect to f, plus s of v, its coefficient vector with respect to f. This was a general statement about coefficient vectors. Good? And now, what is t of v with respect to f? Again, I'm going to use the theorem that did not freak you out. T of v with respect to f is T representation matrix acting on V coefficient vector. And S representation matrix acting on V coefficient vector. This equals this is the theorem that you said you're okay with. Good? So everybody's smiling here. Are you really okay with it? Is it really clear what just happened here? I told you we're going to get a little blurred by slightly heavier notation. But if you see what's going on here, it's really simple. Good? Everybody? Sure. Okay. And one more step and we're done. Now these are matrices. This is a matrix times a vector, or a matrix times a matrix. This is a matrix times a matrix. We can distribute, right? So this equals T EF plus S EF times V E. So what did we show? That T plus S EF times VE is the same as TEF plus SEF times VE, and this was true for any V. Therefore, this matrix and this matrix are the same, and that is what one claimed. Good? Okay, so we should add here, 1 for any V in V.
The last line is commutativity?
Not commutativity. Commutativity would be this. This is distributivity. Think of beyond all the notation here. This is a matrix A, this is a matrix B, this is a matrix C. AC plus BC is A plus BC. That's all that's written there. And we know that holds for matrices. Good? Whew. Good? Okay. So likewise, show this. This is in fact a bit more of a mouthful. Try to show this. Try to show 2. Okay? You need to take a general V sub E here, use this theorem, and pass back. Okay? Good. Okay. Now let's say the similar statement for, so this was the statement concerning addition and scalar multiplication. Now let's say the similar statement concerning multiplication of matrices or composition of the maps. Okay, so it would go as follows. Theorem. So we have V, and then we have U, and then we have W, and let's call this map S, and let's call this map E, T, and we're going to need bases for each of these spaces. So let's take a basis E for V, a basis F for U, and a basis G for W. Okay, so this is the setup. Okay, and all these maps are linear. S, T, linear. So we know there's a composition going from V to W. The composition is called TS, right? And the claim is that TS, tell me if you agree, So then, tell me if you agree that this is the statement. The composition, Ts, goes from V to W, right? The matrix representing this is going to be with respect to the basis of V and the basis of W. So it's going to be Ts, E, G, from V to W. Do you agree? And the claim is that this equals the product, the matrix multiplication, of the matrix representing S and the matrix representing T. The matrix representing T is the matrix T, F, G, and the matrix representing S is the matrix S, E, F. That's what we need to prove. Good? Think. Don't ask. Think first, run it in your head, and tell me if you agree. And then ask.
No, I agree. I'm asking if that's what we did on the examples earlier.
Exactly. Right? We took the matrix for one, the matrix for the other, and we showed that the product of the matrices exactly gives you the composition of the linear maps. Okay? Good? Do you agree that this is what we need to prove? Okay? How are we going to prove it? We're going to take a general vector in V, put it here and put it here, and show that for any such V, these are equal, and therefore the matrices are equal, just like we did in the previous proof. Okay? So is everybody with me? Can you see beyond the notation? Okay, the notation here is slightly, gets in the way, is slightly confusing. Okay, so let's see that. What do we need to show? So proof, we're going to take Ts, so let's start it correctly now, for any V in V, we have Ts, e.g., acting on V, E. Right? And we want to show that this is the same as this acting on VE. Right? So let's start working on it. By the theorem of what is a matrix representation, what it does to a coordinate vector, this is the same as Ts of V, coordinate vector, in which basis? G, in the basis of the range of this map. Right? So this is the theorem of what it means to be a matrix representation. Right? Okay. Now, inside here, we're in the realm of operators, of transformations. We know what Ts of V is. It's T of S of V. And again, this in G. Do you agree? Good? Okay. Now, this is T of something in the base G. T of something in the base G, I can translate to the matrix corresponding to T with respect to the basis of F. S of V is a guy in U, right? So this equals, again, by the same theorem that I used here of what it means to be a matrix representation, this is the same as T, the matrix representing it, F, G, times S of V in the basis F. Take S of V in the basis here, act on it by the matrix representing T, you get T of S of V in the matrix, in the coordinate vector in the basis G of W. Okay? Good? Okay, and again, what is S of V? Same theorem I'm using. I'm not touching this, T, F, G. What is S of V? It's S, its matrix representation, EF, times V, its coordinate vector, E. And we're done. For any vector v, Ts e.g. times v is the same as Tfg SEF times v. So the matrices are the same. Okay? It's heavy. It's a bit heavy, and it's heavy because of the notation. Okay, you have to think what's hiding behind this notation. Get used to the notation. There's no way around this notation. Okay, there's no way to make this lighter. Well, you could say, let's denote this matrix by A, and this matrix by B, and this matrix by C. But at some point, you're going to have to use all these facts, so it's just going to get longer and more confusing because there are going to be more letters. Okay, this is as straightforward as it gets. Okay, good? Okay. Here's a little exercise. See if you can do this exercise. We have the identity matrix, right? What do you think is going to, what transformation is the identity matrix going to be a matrix representation of? The identity transformation, obviously. Okay, then show it. Show it. So I from V to V is the identity map. Right? That sends every little v to itself. Okay? Show that I, its representing matrix with respect to some base, to the standard basis maybe, E is just the matrix I. The matrix I with ones along the diagonal and zeros off diagonal. Okay, show this. Okay. So here's the next theorem. So we discussed the multiplication, which corresponds to composition. We discussed the sum and the scalar multiplication. And the other thing we showed in the previous clip was the inverse. Okay, and again we saw in the example, so let t from v to v linear. So let t from v to v be a linear operator. Somebody asked me over the break, I'm defining inverses only for maps from v to itself. Okay, this can be extended. You can define an inverse for a map from v to w, but it becomes a bit more complicated because you can't say that t inverse is the identity because if this is v and this is w, there's the identity for v and the identity for w. So you have to be a bit more careful. If you do t and then t inverse, it's the same as the identity for v. If you do t inverse and then t, it's the same as the identity for w. And then you're going to have to argue when does the inverse exist and when does it not, and how does it relate to matrices? Is it a question of dimensions? It's a more subtle discussion. For us, it really suffices to discuss invertibility only in the context of operators from a space to itself, in which the corresponding matrix is a square matrix, and then it's A inverse in the regular sense. That's what we're going to prove now. Okay, so for us, we're only discussing invertibility of operators and not invertibility of general linear transformations. Okay? Okay. So maybe let's add let t from v to v be, oh, ugly. Let's rewrite this. So let t from v to v be an invertible linear operator. So it's a linear map from a space to itself, and being invertible we know is if and only if it's either one-to-one or onto, because then it's both. Okay? Okay, then what is the statement? The statement is, suppose E is a basis for V, then the map, the matrix representation with respect to that basis. Remember that when it's the same E, we just write T sub E. Remember we did that before we discussed TEF. We started out with linear operators, and then we said we just write it as T sub E when it's the same space. So TE, sorry, that's not what I want. I want to claim that T inverse with respect to the base E is the same as T with respect to the base E inverse. This is the inverse of the map, and then take the matrix representation. This is the map itself. Take its representation. Now it's a matrix. Take the inverse of the matrix. So the statement is the inverse transformation is represented by the inverse matrix. Okay? Again, do you see beyond the notation that this is precisely the statement that if A represents T, then A inverse represents T inverse? Good? Okay. Let's prove it. Proof. So what does it mean that T is invertible and that T inverse is the inverse map? It means that T inverse is I. That's the meaning of being an inverse map, an invertible map, right? Okay. Therefore, T, the matrix of T, with respect to the basis E, times the matrix of T inverse with respect to the matrix E. This is a product of two matrices, right? This is a product of two matrices. But we know that a product of the matrices corresponds to the matrix of the product. That was the previous theorem, right? The product of the matrices corresponds to the matrix of the product. So this equals T inverse the matrix of the product. It's a simpler form of the previous theorem. In the previous theorem, there was an E, an F, a G, right? There were different bases because it wasn't just all from V to V. Now it's from V to V, so there's only one basis, E, and everything becomes a lot simpler, right? Okay. And what is the matrix that represents, what is TT inverse? It's I. It's the matrix representing the identity map. And we just said as an exercise, this is just I. The matrix I, right? So this matrix times this matrix is the identity matrix. So this matrix is the inverse of this matrix. That's what it means. Now we're in the world of matrices. Okay? So therefore, this matrix T inverse E is the inverse matrix of this, is TE inverse. And that's what we wanted to show. Good? Okay. Questions? Okay. So there's you may need to read this again, and maybe before you read this again, you may need to go back to two things and recall two things. One is our discussion of coefficient vectors, okay? Because we used some facts about them. What is a coefficient vector? Okay? And the other is our discussion of representing matrices. Okay? So what is TEF? Okay? And that theorem that we keep using, that TEF times VE is T of V F. Okay, we keep using it all the time. We used it about 7 times on these 3 boards. You have to recall precisely what it does. Okay, why is it true? And there's really, we didn't, all these proofs were rather short, rather straightforward. It's just easy to drown in the notation. And you have to float above the notation. And for that, you may need to refresh your memory as to what this notation stands for. Okay, good? Okay.
It seems to me a remark or a question.
Okay, go.
Like this proof is missing a step.
Why?
After you show that it equals I at the end, I mean, I think that you might want to show that I equals t times the inverse of t.
So first of all, do you agree that this is a statement above my hand? This is a statement about maps.
Yeah.
The product of t and t inverse, the maps, where is it? T and t inverse. The product is the identity map. It's just like doing nothing. The identity map is the map from V to itself that does nothing. Do you agree? Okay. So now I took the matrix and the matrix, okay, and in between there was some arguments. You believe those. And now I got to a statement about matrices. This matrix, call it A. This matrix, call it B, equals I. AB equals I. The statement that AB equals I means that B is the inverse of A. And that's what I said, that B is the inverse of A. Good? So again, it may be blurred in the notation, but that's all I said. Okay? If you want to be more precise, you may want to show that BA equals I as well, but we know that's not necessarily, that it's not necessary. So if AB equals I for square matrices, the matrices such that AB equals I, BA is going to equal I as well. Okay, that was a statement very, very long ago when we discussed matrices. Okay? Good? No missing step. Sure. Okay, wonderful. Okay, so let's stop this here. There are no examples here because we did all the examples in the previous lesson, right? We did many examples and showed that these things indeed hold, right? That the matrix A representing a transformation T, the matrix A inverse represent the transformation T inverse. We showed it in examples. Now it's just the formal statement that this is indeed the case. Okay? Okay. Yeah, so let's stop this one here.